Analysis design of algorithm for RGPV exam notes are in comments section. Algorithms. 1. Definition. An algorithm is a step-by-step procedure or a set of instructions for solving a problem or accomplishing a specific task. It is a well-defined computational procedure that takes some input and produces the desired output. 2. Properties of algorithms. A. Input. An algorithm must have 0 or more inputs. B. Output. It must produce at least one output. C. Definiteness. Each step of the algorithm should be precisely defined and unambiguous. D. Finiteness. The algorithm must terminate after a finite number of steps. A. Effectiveness. Each step must be computationally feasible and can be executed in a finite amount of time. 3. Examples of algorithms. Sorting algorithms, e.g., bubble sort, merge sort, searching algorithms, e.g., linear search, binary search, graph algorithms, e.g., Dijkstra's algorithm, depth-first search. 2. Designing algorithms. 1. Problem understanding. Clearly understand the problem statement, input, and desired output. 2. Decomposition. Break down the problem into smaller subproblems that are easier to solve. 3. Algorithmic paradigms. Choose the appropriate algorithmic paradigm such as divide and conquer, greedy, dynamic programming, or backtracking based on the problem characteristics. 4. Step-by-step design. Design the algorithm by defining the steps needed to solve each subproblem. 5. Pseudocode, flowchart. Represent the algorithm using pseudocode or flowchart to provide a clear and concise description of the steps. 6. Analysis. Evaluate the correctness and efficiency of the designed algorithm. 7. Refinement. Refine and optimize the algorithm to improve its performance if required. 3. Analyzing algorithms. 1. Correctness analysis. A. Proof of correctness. Use mathematical induction or loop invariance to prove that the algorithm produces the correct output for all possible inputs. B. Worst case, best case, and average case analysis. Analyze the algorithm's behavior under different scenarios to ensure it works correctly in all cases. C. Test cases. Verify the algorithm's correctness by testing it on various inputs, including edge cases and boundary conditions. 2. Efficiency analysis. A. Time complexity. Measure the running time of the algorithm as a function of the input size. Use big O notation, e.g., O(n squared, to express the upper bound on the growth rate of the algorithm. B. Space complexity. Analyze the amount of memory or space required by the algorithm as a function of the input size. C. Asymptotic analysis. Focus on the dominant terms of the time and space complexity to understand the algorithm's efficiency. Notes on heap, heap sort, and introduction to divide and conquer technique. Heap. 1. Definition. A heap is a complete binary tree where each node satisfies the heap property. In a min-heap, for every node, the value of the node is smaller than or equal to the values of its children. In a max heap, the value of the node is greater than or equal to the values of its children. 2. Operations on heap. A. Insertion. Insert an element into the heap while maintaining the heap property. B. Deletion. Remove the root node, minimum or maximum, from the heap while maintaining the heap property. C. Heapify. Rearrange the elements of an array into a heap structure. 3. Applications. Heap data structure is used in various algorithms like heap sort, priority queue, and Dijkstra's algorithm. Heap sort algorithm. Heap sort is a comparison-based sorting algorithm that uses the heap data structure to sort elements in ascending or descending order. It follows the following steps. 1. Build max heap. Convert the given array into a max heap, where the value of each parent node is greater than or equal to the values of its children. Start from the first non-leaf node, i.e., n, 2, 1, where n is the size of the array. Heapify the array by repeatedly calling the heapify function on each node from the last non-leaf node up to the root. The heapify function ensures that the largest element bubbles down to its appropriate position in the heap. 2. Sort the array. Swap the first element, root, of the max heap with the last element of the array. Reduce the heap size by 1. Heapify the new root to maintain the max heap property. Repeat the above two steps until all elements are extracted and placed in their sorted order. Pseudocode for heap sort. Backquote, backquote, backquote. Heap sort, array. N equals length of array. Build max heap. For I equals n, 2 to 1 down to 0. Heapify, array, n, I. Sort the array. For I equals n 1 down to 1. Swap array, 0, with array, I. Heapify, array, I, 0. Heapify, array, n, I. Largest equals I. Left equals 2 asterisk I plus 1. Right equals 2 asterisk I plus 2. If left array, largest. Largest equals left. If right array, largest. Largest equals right. If largest, equals I. Swap array, I, with array, largest. Heapify, array, n, largest. Backquote, backquote, backquote. Time complexity. Building the max heap takes O, n, time. Each call to the heapify function takes O, log n, time. Therefore, the overall time complexity of heap sort is O, n log n, in all cases. Space complexity. Heap sort has a space complexity of O, 1, as it performs sorting in place without requiring any additional space apart from the input array. Heap sort is efficient, stable, and has a consistent time complexity, making it suitable for various scenarios where a reliable sorting algorithm is needed.